3, 2, 1! Happy new topic!
What's your resolution for this topic?
Wow, I just want to make math more radical. What about you?
I just want to be a little more irrational. Anyways, let's talk about rational and irrational numbers real quick. Because once upon a time, like last year-ish, you would have talked about rational numbers. Take a moment, think of what those numbers are to you. And think of some examples that you could put down here. Hopefully you pause and you put some down. Here I go. Some examples of rational numbers could include things like a fraction-y fraction, like 2 over 7. Or just a straight up integer like 5, or even negative 5 if I really wanted to. Or a terminating decimal like 3.6. Those aren't all of the rational numbers, but those are examples of rational numbers. Definitions-wise, we've got a couple here. So a rational number is a value that can be expressed in the form a over b, where a and b are integers, b is not equal to 0, and a over b is fully simplified.
Oof.
Yeah, that's a doozy of definition. The key points, though, are that you can represent the value as a fraction, and that fraction will be fully simplified. In decimal form, a rational number will always terminate or repeat. So if we see something like 3.33333, that is going on forever ever, that is rational. It's possible to express that. But something like, well, I don't know, pi, which is what, 3.1415992, I don't know the rest. It's something like that though. But there's no pattern to it. We don't know what it is. So that can't be rational. And that repetition doesn't have to be necessarily a single digit. Something like, for example, if you take 9 divided by 11, you're going to get 0.818181818181. That's going to go on forever. So that is also a rational number. It has a terminating or repeating decimal. The opposite of that is an irrational number. And that's a value that can't be expressed in this fully simplified fractional form. Somehow I missed the letter y in that definition, but that's okay. So it can't be expressed in this form of a over b, where a and b are integers and b is not 0 and a over b is fully simplified. So if it's not rational, it's irrational. And as a corollary of that definition, it's worth noting that real numbers that are written as non-terminating, non-repeating decimals are rational. So if it terminates or repeats, it's rational. If it doesn't terminate, if it doesn't repeat, it must be irrational.
All right, so we're going to start looking at radicals as this unit kind of suggests. And as we do so, there are some things that we might want to kind of keep in mind. So those perfect squares or even perfect cubes will have square roots or cube roots that will be rational. So for example, 9 is a perfect square, so the square root of 9 will give us a rational square root, okay, which is 3. In the same sense, 8 is a perfect cube, so its cube root will also be rational here. Okay, so our perfect squares and perfect cubes will have rational square and cube roots. What we're going to be doing is we're going to look at irrational numbers called radicals. So those radicals coming from numbers that weren't perfect squares or perfect cubes or perfect fourths or perfect fifths to begin with. When we're looking at a radical refers to this whole thing. And that consists of 3 different parts. So the first part here, this little n value, that's called the index. Okay, so that most often when we see these, the index is usually going to be a 2 because square roots are most common. But the index can be things like 3 or 4 or 5 or 6. They won't be a decimal and they won't be 1. So that index is going to be a whole number that is 2 or larger. This symbol here, that's the radical sign. And the value underneath the radical sign, that number or variable, would be called the radicand. Those three things, the index, the radical sign, and the radicand, together form what we call a radical. Okay. So before, as we were mentioning, I mentioned that the index is very often 2. And in fact, it's so often 2 that sometimes we don't even write the index because it'll just automatically imply that there's a default of 2 there. So for example, if we were looking at the square root of 9, well, that index we didn't write down. Well, that index is automatically going to be 2. If it's not showing, it is assumed that it's a 2. Whereas when we looked at the cube root of 3, because by default, if we didn't write it, it would be 2, but we want to have the 3 there, we have to write that index down.
We're going to be approximating values of radicals, so very non-calculator kind of work. And when we do so, we're going to seek out nearby perfect powers. So if we're looking for square roots, we're going to look for nearby perfect squares. And if we're looking for cube roots, we're going to consider nearby perfect cubes of the radicand. Just for recollection purposes, you're going to want to know some of your perfect squares. For example, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. You can write down or have a reference somewhere for what your perfect squares are, as high as you need to go. And similarly, you're going to want to know some perfect cubes, like 1 to the power of 3. 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. 4 times 4 times 4 is 64. And you can keep going with these things as necessary. But do make sure you can identify perfect squares and perfect cubes. If we wanted to estimate something like the square root of 13, we can note that, well, 13, the radicand, is between 9 and 16. And this 9 and 16 are important because they are perfect squares. Perfect squares because we're dealing with a square root. So since 13 is between 9 and 16, the square root of 13 has to be between the square root of 9 and square root of 16. Square root of 9, of course, is 3. Square root of 16 is 4. So the square root of 13 has to be somewhere between 3 and 4. We might say it's closer to 4 just because 13 is closer to 16 than it is to 9. So it's not like dramatically closer. So we're not too much higher than 3.5. So 3.6 seems to make the most sense. It wouldn't make sense to say something like 3.9 because we're not massively closer to 16 than 9. But somewhere a little bit closer that way.
All right, so we're going to take a look at this next page here, and we're going to approximate each value to the nearest tenth. So again, we're going to use that method that Mr. A mentioned before, is that right now this question is asking us to approximate a square root. So we're going to find the two perfect squares that surround 40. And those two would be 36, which is just under 40, and 49, which is over 40. And I'm going to add these less than symbols in between. And if we know that 36 is less than 40, which is less than 49, we know that the square root of 36 is less than the square root of 40, which is less than the square root of 49. And from here, well, the square root of 36 it's just 6. And the square root of 49, well, that's just 7. So we know that the square root of 40 is going to be approximately equal to, so notice that this symbol here, I'm not writing equal to. I make a little wave or these little squiggles in my equal sign, and that means approximately equal to. Okay, so very key here that we're not using an equal sign. But the square root of 40 is approximately going to be equal to 6 point something. And now if I'm looking at my, oops, that's not a highlighter, my 40, is it closer to 36 or is it closer to 49? Well, it's 6 away from 36 and 9 away from 49. So we know it's going to be closer to the 6 than the 7. So I'm going to say about 6.3. So the square root of 40 is approximately equal to 6.3. Now we're going to try the next one as well. And again, we have a square root. And what I want you to do is see if you could pause and try this next one on your own. And then when you're ready, unpause, and I will be right here, ready to go through it with you. Boop. I think that was maybe the button or the noise.
Yeah, that was the pause button noise. It wasn't me. It was the pause noise.
Is the pause noise going to hit a play noise?
Yeah, no, it was the same button. It was one continuous sound.
Okay, so wonderful. We are back, baby. So we are looking for perfect squares that surround 215. And that would be 196 and 225. And so if I know that 215 is between the two perfect squares 196 and 225, its square root is going to be between those square roots. And the square root of 196 is, of course, 14. And the square root of 225 is, of course, 15. And again, looking to see what's closer. So I know that the square root of 215 is approximately equal to 14 point something, because it's somewhere in between. But what is it going to be closer to? Well, I see that 215 is about 10 away here, and on the other side it's further than 10. So I would say probably closer to 14.7. Okay. One thing that I want you to make sure as we're writing these things down, when you're drawing your radical signs, okay, please make sure that your radical sign continues until the end of the number. So sometimes you'll see people kind of draw those little, I don't know, hook, maybe let's call it, just to ensure that the full number is encased. If you do something like this, obviously maybe you wouldn't have as big of a space. How do I not know that this is square root of 2 times by 15? It adds a little bit more confusion. So we want to make sure that our square root sign or our radical sign completely encases the number. All right. Mr. A, take it away!
Okay. We're going to look at some cube roots and estimate those. You can feel free to try it if you're feeling confident. But the concept is still the same here. 70 is not a perfect cube, but it is between some perfect cubes. If you want to look at a list of perfect cubes and figure that out, cool. Anyways, 64 is a perfect cube. And the next one, 64 is 4 times 4 times 4, so the next one would be 5 times 5 times 5, which is 125. And I'm just now thinking I might need to space these out a bit more, is all. I've got a 64, I've got a 70, and I've got a 125. And because 70, our radicand, is between 64 and 125, we can say that that order is maintained when we talk about their roots. So cube root of 64 and cube root of 125 surround the cube root of 70. Therefore, the cube root of 70 is somewhere between 4 and 5. 70 is notably closer to 64 than it is to 125. So I'm going to say it's about 4.1. My squiggles need work. I'll take those ones. And last of these 4 examples, cube root of 100 is also between cube root of 64 and cube root of 125 still. So we're still between 4 and 5. But this time a bit closer to the 5. So I'm going to say cube root of 100 is something like 4.6-ish.
All right, so we've just looked at these past 4 examples and realized, hey, we can actually figure out their approximate values. And if we can figure out these approximate values, that means we can put a bunch of irrational and rational values or a bunch of radicals in appropriate order, either ascending or descending as necessary. So what we're going to do here is look at an example where we have 5 different radicals. And the question's asking us to arrange these in ascending order, so from least to greatest, by approximating their values. So step 1 here is to approximate the values of each of these radicals. Step 2 would then be put those approximations in order from least to greatest. And then step 3 is, instead of writing the approximations because it wants us to write or arrange the radicals in order, is we need to make sure our final answer is the radicals themselves in approximate order. So what I'm going to get you to do is I want you to pause and just tell me what these approximate values would be, okay, for each of these 5 radicals. So boop, you've paused, and boop, you've come back. Wonderful. And so hopefully you have some sort of approximation for each of these. Keep in mind that this is a calculator-free unit. So please, please, please make sure that you're not using your calculator to figure out the actual value of each of these. That will be of no use to you of any assessment. So make sure you're practicing your approximations. So if you have gone ahead and done this, we would have gotten the square root of 30 to be, approximately 5.5. The cube root of 100, well, you actually just did that. So you got 4.6 here. The square root of 24, that's almost 25, which is a perfect square. So let's say 4.9. The fourth root of 625, that's actually a perfect fourth, I guess. And that's 5 on the button there. And the last one, we're looking at the cube root of negative 100, which means our final answer here would have to have been negative, right? Because if I'm looking at a number that is multiplied 3 times, or by itself 3 times, to give me a negative, well, a negative times a negative times a negative will give me that negative value. So I get negative 4.6, right? Because if this was positive 4.6, this is negative 4.6. Same thing except a negative sign in there. All right. So hopefully you did those approximations on your own and you're feeling decently confident with them. But what we're going to look at now is the question's wanting us to write these numbers in ascending order, so from least to greatest. So I'm going to go ahead and take these approximations and order them. So negative would be the smallest, negative 4.6. Then we'd have 4.6, then 4.9, then 5, then 5.5. Okay. The question again didn't ask us to order the approximations. The question asked us to order the following values. So these guys from least to greatest. So realistically, the step is optional here. I like to do it because it helps my brain put things in proper order. But I'm now going to go ahead and write the final answer. So negative 4.6 was an approximation for the cube root of negative 100. Okay, 4.6 was the cube root of positive 100. 4.9 was the square root of 24. 5 was the fourth root of 625. And 5.5 was the square root of 30. One last thing I will mention here. Well, actually, hold on. Let's finish this. This is my final answer. We're happy. We're great. Okay. One thing I do want to mention, just something that I notice very often, is when we're writing some sort of radical and we're using the index, please make sure that your index isn't the same size as your whole number. The index is almost like a superscript or like the size of an exponent, right? So it's little itty bitty and it fits within this little kind of nook and cranny of the radical sign, and then you write your radicand. And again, the radicand is completely encased by that radical sign. All right.
Next example, give it a try. Now that you know how to approximate some radicals, one of these might be a little tough to approximate, but see what you can do. I am going to just jump in here. 5th root of 30. Well, if I'm thinking of numbers, 1 times 1 times 1 times 1 times 1 is 1. Next one, 2 times 2 times 2 times 2 times 2 is 32. So this has to be like 5th root of positive 30 would be a little less than 2. I'm going to say this is close to like negative 1.9-ish. Cube root of 12, somewhere between, well, 12 is somewhere between 8 and 27, so the cube root must be, like, say 2.3-ish. 12 is closer to 8 than it is 27. 6 over 5 we can get right away. That's just straight up 1.2, noting that these are all negative. Cube root of negative 1 is negative 1. Whoa, this thing! 5th root of negative 0.9. How are we going to figure that out? Well, it's worth noting that if we take 0.9 and square it, we're going to get something smaller. And if we take 0.9 and cube it, we're going to get something even smaller than that. So smaller and smaller and smaller. What that tells us is that for all these numbers between 0 and 1, the square root will actually always tend to be higher. Right? Like the square root of 0.25 is actually 0.5, which is a bigger number. In that same sense, we must get something that's more than 0.9, but it has to be less than 1, because as soon as we go higher than 1, numbers start inflating. So I don't know what this is exactly, but it's between like negative 0.9 and negative 1. Reordering, least to greatest, ascending order, so least to greatest. Least is negative 2.3. Then we've got negative 1.9, negative 1.2, negative 1, and then this thing that's like 0.9 something. Which means for final answer purposes, we've got the cube root of negative 12. I can do better. That's real swoopy. Sorry. We've got the 5th root of negative 30. We've got negative 6 over 5. Yikes. The cube root of negative 1. And the 5th root of negative 0.9. That one is done.
All right, the last thing we're going to be doing is just trying to state whether a given number is rational or irrational, and we're going to kind of explain why your answer is such. Keep in mind that when we're looking at radicals, a radical will only be rational if the radicand is a perfect square or a perfect cube or perfect fourth or perfect fifth, depending on the index. Okay? If it is neither of those things, then it would then be considered irrational. All right, so we're going to take a look at this first one here. We have the square root of 19. Well, 19 is not a perfect square, and as such, it would be considered an irrational number. Irrational. Why? Because 19 is not a perfect square. All right, that's it. That's the first one. We're going to move on to the second one here. Negative 4 over 7, is that rational or irrational? Well, this, my friends, would be rational. Why? Well, it's in a fractional form, and that's what the definition states. It's in the A over B form where B does not equal 0. Right? And that's the exact definition. So it fits the definition, thus it is rational.
These next ones have some fractions involved, but we can deal with them by noting same as with the exponent laws, where you have a over b to the power of something. That's like taking that power of both the top and bottom. Same. This cube root can apply to the top and bottom. And by that logic, we can say that this one is actually going to be rational. And that's because this top piece, cube root of 27, is rational, since 27 is a perfect cube, and 125 being a perfect cube is thus, it thus also makes cube root of 125 a rational number. So this whole thing is rational because both 27 and 125 are perfect cubes. And the last example of the day,
Give it a try.
there it is. And we can look at this and say, if we want, we've got cube root of 64 over the cube root of 49. And while this part is rational, because we can take the cube root of 64, we can't take the cube root of 49. So what that does is makes this whole thing irrational.
Ooh, the cube root of 49, I feel like that always gets people because
Yeah.
you're like, oh, 49, it's a perfect square.
Yeah.
But you gotta check that index. 49 is not a perfect cube. Dang. If you want to look at some practice work to kind of brush up your skills and make sure you really got this set, at the bottom here, there's some textbook suggestions. Otherwise, that's it for all. That's it for all.
That's it for all.
That is it for now. I hope you have a fantastic math-filled and radical day.
Bye.